right, so following up on the vertex form issue, in this example, we'll be starting with a given equation that is already in vertex form, yes, and we just need to identify information from that and draw a graph. So here we are, we have y equals 3 times x minus 5 squared minus 4. The 3, the importance of the 3 is that it's positive. It's a positive, so our parabola would be facing upward. Then we can identify the vertex. Well, notice in blue here what I did, and this is how I do things when I'm either learning math for the first time or just rehearsing or reminding myself, is to write out all the general formulas for each problem. Every time, just to do it all. I always write down the basic formulas and keep it straight. So here we have h is the 5 and the k is minus 4. Therefore, the vertex will be the hk, which in our case will be 5, negative 4. And the line of symmetry, which I'm abbreviating as ls, is x equals 5. Remember, the line of symmetry, or as the textbook calls it, the axis of symmetry, the x value of the vertex is the basis for x equals, it's the line of symmetry. It's always the same. So notice how I've graphed this. We're getting a basic graph going here. Please do label the vertex as I've done here, and write in your axis of symmetry or the line of symmetry. And so I have it abbreviated there as ls, x equals 5. Let's see. I think that's good. Now let's take this graph and extend the ideas in the following way here. Now this is giving more complete information. It is going back to chapter 2 in a way, but here we are in green in particular. What we're trying to identify in part is, where is the graph decreasing, where is it increasing? What does that mean? Well, a decreasing graph means as you go left to right, the graph will be falling. If you're going left to right, the graph is falling, that's decreasing. If you go left to right and the graph is increasing, or going up I mean, it's called increasing. So there we are, it's decreasing, the graph is decreasing from negative infinity up to 5, not including 5, ever. So the valley here, that very point on the very bottom there, the vertex, you don't include that x value. Okay, so that's why you have a, we call it parenthesis. Then afterwards is increasing. So there you get 5 to infinity. So if that's okay, it follows really by definition that we have a minimum value of the function. And try to keep this straight. Minimum value of negative 4, which is the y value, at a particular x value, x equals 5. Okay. But if that's okay, that we have this minimum value of negative 4, the range kind of comes out automatically. The range will be negative 4 and everything above. That is negative 4, including the number negative 4. Y equals negative 4 is a point on the graph, up to infinity. So there's a close connection between the range and the minimum or maximum value. And from that all comes from your intervals of increasing or decreasing. It's actually very tidy. Maybe takes some getting used to, but it's actually very tidy. Now let's look at a couple of other examples. These come from before, the examples before, but now with this additional information we're trying to get out of them. So here in this first example, we have y equals x minus 3 squared plus 4. From our earlier work, we saw the graph as looking like this. Notice that we have our line of symmetry going right through the vertex, as it always should. As a reminder, our line of symmetry will always be a vertical line, always vertical, because we're dealing with functions here. Now, the new part was determining where, on which x intervals, the graph is increasing or decreasing. So the way I'm marking it out here is decreasing on negative infinity up to, but not including 3, increasing afterwards, 3 to infinity. If that's okay, then we say, great, the minimum value, and it has to be a minimum value, is the y value, minimum value of 4 at x equals 3. and that minimum value of 4, that phrase really makes the range interval. It may not be quite so obvious, but it really does necessitate that the range will be 4 to infinity. However, I should say one value of writing the graph kind of early as you can, which will be part of the procedure I'll emphasize later, is that you can look at the picture. You can look at the picture and verify where the range is. And in these problems, we're just concerned with range, not with domain. Domain's everything. Parabolas are very nice in that respect. The domain is all real numbers, but the ranges are not. So there you are. The second example I have towards the bottom of this page here is well, it's looks like the reflection of the top, which it really is. But notice that the number in front of our squared is negative 1, so the graph is facing downward, frowny face and all that. And this is a graph we had done earlier in the earlier video. But the new information was increasing from the left, decreasing towards the right there. You have a what do you call it, a peak, the high point. We're increasing, the graph is increasing from negative infinity up to x equals 3, decreasing afterwards, decreasing on 3 to infinity. And from that fact, it turns out, again, basically by the definition of a maximum value in this context, the maximum value is 4, notice the y value, at a particular x value, x equals 3. And from this, or if you like from the picture, both are consistent, right? The range will be all numbers below 4 up to y equals 4, which in interval notation would be negative infinity up to and including 4. Okay, so that is fleshing out a little bit more information about these graphs. And we're getting there about all the complete information that we're going to be needing in 3.3. There's a bit more to come, but that will be for the next video, which will be how to connect up these vertex forms with what's called the standard form of a quadratic. All right, thanks very much.